Hi, my name is James, and today I'm going to teach you how to use the method of separation of variables. You can use the method of separation of variables to solve first-order differential equations that meet the general form. The general form of separation of variables is the first derivative with respect to your independent variable is equal to a function of your dependent variable times your function of your independent variable. So in this case, it'll be the derivative of y with respect to x is equal to a function of y multiplied by a function of x. And the steps for separation of variables are going to be as follows. So once it meets the general form, you're going to separate the variables. It seems a bit obvious, but that's why we call it separation of variables. So the first step that you're going to do is you're going to separate your y's and your x's on each half of the equal sign. And then what you're going to do is you're going to integrate both sides of the equation. And then step 3 is going to be solve for y. So now that I've covered the definition of it, we're just going to go over a couple example problems. So our first example will be one of the simplest forms. So it'll be dy dx is equal to x times y. So I've given you an equation, and we know that it fits the general form because we have a function of y, which is this, and then multiplied by a function of x, which is just x. So we're going to follow our 3 steps. So first step is to separate the equation. So what I'm going to do is I'm just going to divide both halves of the equation by y, and I'm also going to multiply both halves of the equation by dx. So I'm going to do both of this at the same time here. So this will give us, you have dy, and then I've divided this by y. And since I multiplied out the dx, it's not on the left-hand side of the equation anymore. And then we have x. We've divided the dy, but we've also multiplied by dx. So now we have dy over y is equal to x dx. So we've completed step 1 successfully. This is step 1 right here. Step 2 is going to be to integrate both halves of the equation. So this will be integrate 1 over y dy is equal to the integral of x dx. So let's integrate the left-hand side of the equation first. This is just a property from calculus. The integral of 1 over y is the natural log of the absolute value of y plus a constant. We'll just call this c1. And then the integral of x is going to be x squared over 2 plus another constant. We'll call this c2. And what I'm going to do is, since c1 and c2 are arbitrary constants, we don't actually know what they are yet, I'm going to subtract c1 from both sides of the equation. So now we have minus c1 on the right-hand side, and we're going to combine both of these, and we're going to call this c3. And I'm actually just going to, instead of calling it c3, since it's still an arbitrary constant, we don't know what it is, we're just going to call it c, just to keep things simple. So we have the natural log of the absolute value of y is equal to x squared over 2 plus c. So now, since we've completed step 2 successfully, right here, this is step 2, we just need to solve for y. So we're going to raise both sides to the e power to get rid of the natural log. So this is going to be absolute value of y is equal to e to the x squared over 2 plus c. And this is a property of multiplying exponents. If you have addition in the exponents of a base value, you can instead write this as the multiplication of 2 exponents with the same base value. So this is e to the x squared over 2 times e to the c power. And like I said earlier, e to the c, or I guess c itself is just an exponent that we have. C itself is an unknown constant. So what I'm going to do is I'm going to replace e to the c with just c, because e to the c power is just a different constant. We'll call it c4, and it's arbitrary, so we can just write it as a constant. So now we have e to the x squared over 2 times c is equal to y. So y is equal to plus or minus c e to the x squared over 2. And plus or minus c is just a positive or negative constant, so I can actually get rid of the plus or minus, and we can just have c e to the x squared over 2. So now let's do another example. So we have dy dx is equal to 2xy over 1 plus x squared. So let's see if this fits our general form of our equation. So we have a function of x times a function of y. Let's see if we can separate this into two functions here. So we have a function of x right here. Sorry, we have a function of y right there, and then the rest of it will be our function of x. So let's see if we can separate these. So what we'll do is we'll divide both halves of the equation by y and multiply both halves of the equation by dx. So this will be dy over y is equal to 2x over 1 plus x squared dx. So we've separated y and x successfully. So now what we're going to do is we're going to integrate both halves of the equation. So this is going to be natural log of y, and I'm not going to write the absolute value bars because we're going to get this plus or minus issue over and over again, and it's going to factor into the unknown constant, so I'm not going to worry about it. So we just have natural log of y is equal to, we have the integral of 2x over 1 plus x squared. So this is going to be a u substitution problem. So this is going to be the integral of 1 over u du, where u is equal to 1 plus x squared, and then du is equal to 2x. So these are both equal to each other. So this is just going to be the natural log of u plus c, which is just the natural log of 1 plus x squared plus c. So to rewrite this is the natural log of y is equal to natural log of 1 plus x squared plus c. So now I'm going to raise both sides of the equation to the e power. So this is y is equal to e to the natural log of 1 plus x squared times e to the c power, because we have addition in the exponent again, and the natural log is going to cancel out, so this is just 1 plus x squared, and then e to the c power is just another constant, c. So now we have y is equal to c times 1 plus x squared, and this is our answer. Okay, so let's go back and just review our steps just so that I can make sure that we covered this. So here we have step 1. Here I will do this. Here we have step 1. Wow, that's ugly. So first thing we're going to do is make sure that it's separable, and what we're going to do is we separated it into dy over y and then 2x over 1 plus x squared. And then, so this was step 1. Step 2 was to take the integral, which resulted in this phrase right here. And then step 3 is just to solve for y. So we performed all 3 steps there. So let's do another example. This is going to be dy over dx is equal to 1 over y. So here we're looking for a function of y and a function of x, just like I said up here. We don't have any x's in this right-hand side of the equation, so we're just going to let 1 be our function of x. So this is like saying, this is like saying 1 over y times 1, where 1 is our function of x and 1 over y is our function of y. So now we're going to separate this. We're going to multiply both sides of the equation by y. So we have y dy is equal to 1 dx. So we've separated it, and now we're going to integrate. We have the integral of y dy is equal to the integral of dx. So the integral of y dy is y squared over 2. And then the integral of a constant is just x. So now we have x plus c. And now we're going to multiply both halves of the equation by 2. So this is 2x. And then 2 times c is just another constant, 2c. So we'll just leave that as c. And then we're going to take the square root of both halves of the equation. So this is the plus or minus square root of 2 times x plus c. And that's our answer. So here we have 3 mathematical examples of separation of variables. And now I'm going to move into a real-life example of separation of variables. So let's say we have a population, and we know that the rate of change of this population is, let's see, population is p, and it's going to change with respect to time, and this is just a constant times the population itself. So if you have like a petri dish full of bacteria, the rate of growth of the bacteria is dependent on the number of cells of bacteria that are in the dish. Or let's say you have a bank account, the amount of interest that you gain in your bank account is dependent on the current amount of money that you have in the bank account. If you have a population of any amount of animals can usually be represented with the same population growth method. You can also use this for population decay, and I'll show you how to resolve this right here. So here we have a separable equation. We're going to separate this, so we have the derivative of the population over the population is equal to a constant k times dt. We're going to integrate both sides, and now we have the natural log of the population is equal to time times the constant plus another constant c, and then this is population is equal to, I'm raising both sides of this to the e power to get rid of the natural log, so we have e to the kt times e to the c, which is just c e to the kt. So now we have two unknown variables. We have p of t is equal to a constant e to the kt. We have two unknown constants in our final answer. And this equation right here, you're probably going to see this quite a bit in your life, is the equation for population growth and decay, or exponential growth and decay. So what we need is we need two initial values. We need two values to find out what c and k are. So here I'm going to give you two values. Let's say that our population at 0 is equal to 100. So let's say we have 100 people at time 0. So now we need to find c or k based on this value. So we have p of 0 is equal to 100, which is equal to c times e to the 0k power. Anything times 0 is 0, so we just have c e to the 0 power, and anything to the 0 power is 1, so this is just c. So c is equal to 100, and c is our initial population. So if we rewrite our equation now, we have p of t is equal to 100 e to the kt. So now we need another point. Let's say t is days, so after 3 days, our population is now 150. So now let's plug in our value and see what we get. We have p of 3 is equal to 150 is equal to 100 e to the kt. Sorry, t is going to be 3 in this case, so 3k. 100 e to the 3k. And now we're going to solve for k, so we have 150 over 100 is equal to e to the 3k. So we have 3 over 2 is equal to e to the 3k. Sorry, I wrote t here, I meant to say k. So now let's take the natural log of both sides of the equation. So natural log of 3 over 2 is equal to 3k, because the natural log of e cancels it out. So here we have 3k is equal to 0.405. So now now k is equal to 0.1352. We'll just round it to 3 digits actually. So now if we plug this back into our original equation, we have p of t is equal to 100 e to the 0.135 t.